Hello, my name is Kate Schutz, and today I'll be giving a presentation of my Lab 2 experiment. First, I will give a short introduction of the experiment, then I will show some observations and data, the code I used to make the computational model, and give a short conclusion. The purpose of this experiment was to analyze the motion of a large rope swing using initial conditions given. I used two fundamental principles in this experiment, Newton's second law and the energy principle. I also used Hooke's law. I used several equations in this experiment, including the position update formula, the velocity formula, the force of gravity formula, and the spring force formula. The initial conditions were found through a behind-the-scenes video of the rope swing that was analyzed. A computational model was then created to predict the ideal motion of the rope swing. The initial conditions I used in the code were that the initial velocity is equal to the vector 0, 0, 0, the initial time is 0 seconds, the initial position of the individual is negative 45.72 meters, 0, 0, and the mass is 62 kilograms, which is the average mass of a person worldwide. I also used the gravitational constant and the period of 8 seconds. In order to correctly predict the motion of the swing, I need to create a model in which the rope is represented mathematically by an ideal spring. An ideal spring does not have any change in length, so the relaxed length of L naught, which is L0, is equal to the length of the spring L. The length of the spring L is equal to 45.72 meters. Ideal springs also have high spring constants, so I set K equal to 5,000. On this next slide, I have the first part of my code displayed. I started with the code used in Lab 4 and then edited this code to fit my purpose. First, I put in initial conditions. On lines 47 through 51, I calculated the mass of the individual as well as the initial position and velocity of the person. Then, on lines 68 through 69, I set the initial time and change in time. On lines 78 through 84, I put the initial condition of the gravitational constant, the spring constant, and the relaxed length of the spring. I wrote equations on line A, 7 through 89 that correlate with the spring force formula and help calculate the energy of the system later in the code. On lines 92 through 95, I coded several equations that align with the energy principle and calculate the system's energy. On lines 113 through 125, I created the equations in my code that follow the principle of Newton's second law and calculate the object's momentum and velocity. From lines 28 through 130, I wrote a code that finds the length, direction, and stretch of the spring according to Hooke's law. On lines 136 through 143, I again wrote equations that correlated with the energy principle and calculate the energy changes in the object and spring. And then on lines 146 through 149, I created a code that plots the kinetic energy, potential gravitational energy, potential spring energy, and total energy on a graph. In this last part of the code, I updated the time equation on line 163 and put the rate equal to 500. I also made two arrows that represent the spring force and gravitational force on lines 175 through 181. Here's my code. The black arrow is the gravitational force, and the blue arrow is the spring force. An important question to answer is whether or not the motion of the swing adheres to the momentum principle. To answer this question, I need to look at the results of my code. In this graph, the change in kinetic energy is represented by the blue line, the change in gravitational potential energy is represented by the red line, and the change in spring potential energy is represented by the green line. Also, the orange line shows the change in total energy of the system. The swing model adheres to the energy principle because the change in total energy is 0. Also, when the kinetic energy is at its maximum value, the potential energy is at its lowest value. This observation also conforms to the energy principle. In conclusion, I was able to successfully predict the motion of the rope swing with certain initial conditions, if I treat the rope as a spring with ideal conditions. And I was also able to show how the computational model adheres to the energy principle. Thank you.